Okay, so welcome back, everybody. So let me start with a recap of where we're at. So yeah, we're in this section about talking about general semi-simple Lie algebras. And so really everything that we're doing now is the same steps as what we saw for the SL3 case. Okay, so we have this sort of compression of the data associated with the Lie algebra, determined by two choices. Okay, so the first choice is the choice of Cartan subalgebra, H sitting inside G. It's an abelian, it's a maximal abelian self-normalizing subalgebra. There's choices there, but they're all rather related to each other, okay, in a controlled way. But for any such choice, you have this data of the root system. Okay, so roughly their eigenvalues associated to the action of H on G. Okay, but then there's also this pairing that comes from the killing form on the Lie algebra G restricted to H. Okay, and so this is important because it gives rise to geometry on the space of roots or eigenvalues. Okay, so we'll go into some more detail today about these root systems. Second choice is once you have that choice of H, then amongst those roots, you choose a nice basis. Okay, this notion of a base. So it's basis plus some other condition. And there is ambiguity there as well, but again, it's nicely controlled. Okay, so but given those two choices, then you get the Cartan matrix. Okay, this is independent of rescalings of this this pairing here. Okay. So, and it's also independent actually of these two choices. Okay, so you get this canonical process from G going to this Cartan matrix. Okay, this is actually kind of a back and forth correspondence. So to write it, to express this as the Dynkin diagram. Okay, and so you get examples like this. And so eventually, after a bit more work, this leads to the following classification of simple Lie algebras, okay? Complex simple Lie algebras. Okay, and this is a beautiful, beautiful result. I mean, it's really one of the gems of 19th century mathematics. So it was first attempted through Wilhelm Killing, I guess the 1880s or so. But there were some errors there, or rather there were some questions about how rigorous it was, and so Cartan cleaned things up. Cartan's PhD thesis was a rigorous rewriting of this theorem. Okay, in particular, in the original version, Killing's version, there were actually two simple Lie algebras of dimension 52, but Cartan showed that they were actually isomorphic. Okay, so you have these. This wonderful list, extremely useful over the last 100 years and influenced a lot of really interesting mathematics. So you have these classical simple Lie algebras, okay, expressed through their Dynkin diagrams. And then you have so-called exceptional Lie algebras, okay, 5 of them, exactly 5 of them. Okay. So we're not going to go through the details of the full classification, although it's really not that much more of a stretch beyond what we are going to be talking about. Okay, let me just recap for you some of the things. Okay, so actually one important thing to come out of this is that, for instance, from one of these Dynkin diagrams, right, you could get the corresponding Cartan matrix, and then you could understand between the simple roots what the relative lengths are and what the angles between them are. Okay, just using these formulas that we derived last time. Can you remember the bond in between these nodes is the product Cij Cji, and this is heavily restricted, so it could be either 0, 1, 2, or 3. Okay, it has to be integers, these positive integers. Okay, so that's the classification. So today I want to go into some more details about root systems in general, and then a little bit more about their diagrams, throw some nice pictures at you, and then we'll, in the last hour, talk about the theorem of highest weight. And really, it's just the same statement that we did for the SL3 case. So really, I would just want to give you some examples of fundamental irreps more generally in these classical cases. And of course, once you have these fundamental irreps, then you could build up more general irreps using the same construction as we did for SL3. Okay, namely, you look in these higher tensor powers. So if you know the fundamental irreps, then constructing the more general irreps is derived from that. Okay, so before we dive into root systems, let me just reinforce this transition from matrix language to the abstract Dynkin diagram Cartan matrix picture. Okay, so there were several of these examples in the notes, and I asked you to have a look at these. So let me just summarize the situation for C2 or SP4C, because this will come up again as a running example, a few more times in this lecture. Okay, so SP4C is the space, the Lie algebra, which infinitesimally preserves a symplectic bilinear form. Okay, so skew symmetric guy that I'll take to be of this form. Okay, 4x4 matrix. It's skew symmetric with those entries like that. Okay, so if you express the invariance condition, namely M transpose omega plus omega M is equal to 0, then you're going to get this Lie algebra that's given right here. Okay, so it's a 10-dimensional Lie algebra. And then if you look at the diagonal and how it acts, then this tells us some eigenvalue information, just like we did for SL3. Okay, so you get these eigenvalues appearing in this calculation over here. Okay, and notice that this is the Cartan subalgebra. So it's more, even though you're in 4x4 matrices, because of this infinitesimal invariance condition, the diagonal just consists of, it's just two-dimensional. Okay, so H1, H2, minus H1, minus H2, minus H1. And so the natural epsilons to basic functionals to introduce are just, pick off the ith entry. Okay, so there's two of them. Okay, so epsilon 1 and epsilon 2. Okay, so from, for example, this information, then the basic functional, the basic root, epsilon 1 minus epsilon 2 comes out. But then you look also here, and then a different root, namely 2 times epsilon 2 comes out. These other ones, for example, H1 plus H2, so that also appears here. Okay, so that's obtained by summing these guys over here. So the root associated with that would be alpha 1 plus alpha 2. Okay, the corresponding eigenvector or root vector would have a 1 wherever you see B1, so in two places, and zeros elsewhere. Okay, so that's this, the eigenvector is a 4x4 matrix. So that's alpha 1 plus alpha 2. And then this last one is going to be, I guess, 2 alpha 1 plus alpha 2. Okay, so those are the positive roots. Then you have their negatives below the diagonal. Okay, so that's the positive root system, and then the full root system is that and its negatives. The corresponding z's, so these are the dual basis to the simple roots. So that's given right here. So you check alpha 1 and z1 is 1. Okay, so this one minus this one is 1. This one evaluated on this is 0. Okay, and similarly, this alpha 1 on z2, so this minus this is 0. Whereas this on this gives 1. So this is dual basis. Exercise computes the killing form on these entries. So you get this 2x2 matrix, compute its inverse, and then you get the Cartan matrix using the formula alpha I paired with alpha j check under the pairing. So that gives you this. Okay. These relative lengths. Okay, so you use this formula that we derived over here, that this one is root 2 times this one. And then the angle between them is 3 pi by 4. Okay, so the second one is longer than the first. So we have this over there. The product here is 2. So I have a double bond. And then it's directed from long to short. So the arrow is in that direction. Okay. Here's the actual root diagram. Okay, so you have alpha 1 making an angle of 3 pi by 4 with alpha 2. And then you start acting on this guy with alpha 1. So you get alpha 1 plus alpha 2, and then 2 alpha 1 plus alpha 2. And then the corresponding negatives. Okay, so you're appearing on, all the roots are appearing on a square. Then you have the 0 weight in the middle. Okay, so that's the C2 root diagram. Okay, analogous to the SL3 root diagram that we saw earlier. Okay, so I want to go in this first hour to properties of root systems. Okay, just enough. So all of these are not difficult to prove, and we're gonna do it right now. But the end goal here is to be able to talk about the existence of these SL2 triples, which were a running theme in several of these lectures. Okay, so let's go through some some of these properties are. Okay, so given alpha and beta, either a root or 0, and suppose that alpha plus beta is not 0. Okay, then the killing form on that the G alpha and G beta space is 0. Okay, these are orthogonal. Pictorially, what this is saying is, for example, take this as alpha. Okay, if I were to take something other than this one as my beta, okay, lying right opposite it, then these guys are going to be orthogonal under the killing form. Okay, so all the interesting stuff for the killing form is going to be, for a given choice alpha, it's just going to be contained in the minus alpha direction. Okay, and that's what this next part of the proposition discusses. Okay, that you have a non-singular pairing on G alpha and G minus alpha. That's where all the action is happening. As a consequence, so if alpha is a root, then you could also show that minus alpha is a root. Okay, that's obvious from this C2 picture. Okay, so you have this symmetry undertaking negatives. Okay, and that's not coincidence. So it's very easy to prove. Even though B, this guy is non-degenerate by this Cartan criterion that we mentioned before, namely on semi-simples, this is non-degenerate. There's this other step that I never proved, but just stated, namely when you restrict this to H, as we've been doing in all these calculations, this is also still non-degenerate. Okay, and that's important because this is what gives rise to geometry. Next, H star is the span of all these roots. And then lastly, how if you pair vectors from opposite root spaces, then how this is expressed. Okay, so in terms of the killing form, and then this dual vector to alpha. Okay, so let's prove a few of these. Okay, so the first one, remember what the killing form does, right? It takes something in this guy and something in this guy, and then you're supposed to take a trace. Okay, so what is this doing? It sends somebody in the G gamma root space, and then it sends you into this space. Okay, maybe 0. Okay, but that's what bracketing with something in the G beta root space and bracketing with something in the G alpha root space, where you're going to land. Okay, so but if this is going to make a contribution to the trace, then you want this to be, well, basically gamma itself. So if beta is not equal to alpha, so if this is not 0, then you're somewhere else. Okay, so you're not going to get any contribution to the trace. So since beta is not equal to alpha, we get no contribution to the trace. And that's it. Okay, we get this orthogonality property. Property 2. Okay, so if alpha is over here, then B is non-singular. What does that mean? So if I take an element from G alpha, it says that's non-zero. It's saying that there is some non-zero element from G minus alpha for which this pairing is going to be non-zero. Okay. To be singular means you take a non-zero element here, and then for every guy over here, it pairs to 0. Okay. But we already know from part A that, well, these guys are all 0. So, and we have the root space decomposition. So the only thing that's left that could be potentially non-zero is G minus alpha. Okay, so, but we also know that B is non-degenerate. So there has to be something non-zero that pairs with it. Okay. So this follows from A, the root space decomposition and non-degeneracy of B. Okay, i.e., if you have a non-zero element over here, then you have to have it that this is non-zero. Okay, so that's coming from non-degeneracy of B. That's Killing's, that's the Cartan criterion. Okay, so this, oops, ooh, okay. So we have B, okay, and we have A. Okay, so if alpha is a root, then minus alpha is a root. So this is a direct consequence from B, because to say that minus alpha is a root is to say that this space is non-zero. Okay, but that's exactly what we have from B. Okay, so I'll just put D is also a direct consequence of B. Okay. Namely, in this case, you're using that alpha would be 0. Okay, use B and G0 is H. Okay, so direct consequence of B. Okay, so we just have a couple left, and again, they're pretty short. So let's just go through it. Okay, so H star is the span of delta. Okay, the roots. Okay, so I mean, you could assume that it doesn't span the entire thing, but let's just go ahead and so delta is a bunch of things in H star. So that's we can take its annihilator. Okay, so those H's that are 0 for every, when paired with any root. Okay, so given something in here, okay, so if I know that it pairs with every root to be 0, then if I bracket this with the corresponding root space, then I'm going to get 0. Okay, but remember the root space decomposition says that G decomposes into H plus all these root spaces. Okay, but if I bracket an H with these guys, well, that's 0. If I bracket with anything over here, that's also 0 because of this condition. Okay, so root space decomposition implies that H commutes with everything in G. So in particular, you're going to bracket, well, the pairing with the Cartan subalgebra is going to be 0. Okay, but we just showed that this guy is non-degenerate on H. Okay, so therefore, H is equal to 0 by D. Okay. So therefore, the annihilator is 0, and therefore the span of all these guys is all of H star. Okay, so nice application of just root space decomposition. Okay, and lastly, let's show this thing about the bracket. Okay, so this claim over here. Okay, so if I take a root space, take its opposite root space. Okay, I take root vectors in those root spaces. If I bracket them, then you get this expression over here. Okay, so okay, so we have this guy. We want to show that it's 0. Okay, so for any element of the Cartan subalgebra, invariance, we have this nice invariance of the killing form. So let's just write that out. It says that if we act with an X, okay, so invariance means this, okay? So please stop me if you have any questions, okay? So we're going to use this invariance condition, okay, to show that this V is 0. Okay, so let's write this out. Okay, so we're going to eventually use this invariance and I guess non-degeneracy. Yeah, non-degeneracy. Okay, so I'm just going to rewrite. So this condition, okay, so this is B, Y, X, H. X is, yeah, so X is from the G alpha root space. So we know how H acts on it. It acts on it via an eigenvalue, namely alpha of H. Okay, I'm going to pull this out, this number. Okay, and let's see. Byx is the same thing as bxy. This alpha of H, okay, I have this functional evaluated on H, okay. I could rewrite it in terms of the killing form, in terms of the corresponding vector H alpha. Okay, so H alpha, remember, is this corresponding vector under this musical isomorphism, right? Because you have this nice non-degenerate pairing, B. Okay, but this is just a number. This is a number. Okay. So now I'm going to shove it back in. So B. So we have this evaluated for arbitrary H equal to this evaluated for arbitrary H. So let's put them on the same side. So you get V paired with H is equal to 0. Okay. But this guy is non-degenerate. So therefore, V is equal to 0. Okay, so we have all these nice properties. Okay. In particular, this last one is going to allow us to establish the existence of these SL2 triples. Okay. So namely, you could choose an X over here and choose a Y over here such that this is non-zero. And then I could, of course, rescale this or this as I want to, to get rid of this. So, or to normalize it to an H. Okay, so let's just state that results. Let's see. Embedded SL2s. Okay, so for all roots, there exists a root vector, another root vector in the opposite root space, and a corresponding H okay, such that E alpha, H alpha, E minus alpha. So this is our like our X, H, Y in previous language. Okay, is a standard SL2 triple. Okay, so we're just using these properties above. So we're going to choose this guy so that you get this bracket relation here. Okay, which is one of the bracket relations for SL2. So we just need to verify the other ones. So how does this H alpha act on E alpha? Okay, so we want this to be 2 times E alpha. Okay, so we'll do the calculation here. So how does this H act on this? It's by the scaling where you pair alpha with H alpha. Okay. But from the definition, this is really just H alpha check. E alpha, which is 2 E alpha. So similarly for E minus alpha, you're gonna get you're going to get H alpha, E minus alpha is minus 2 E minus alpha. Okay, so these are all yeah, these are SL2 triples. Say this for later. Okay, other things. Okay, so we have these nice SL2 triples, and right, that really gives rise to something that was stated before, but let's just formulate it as a proposition here. Okay, it's because of the concept, because of the existence of these SL2s that you have these integrality conditions. Okay, so for any 2 roots, we have beta paired with alpha check to be an integer. And we'll see the relevance of this integrality condition. So this is called the so-called, oops. So-called crystallographic restriction. Okay, so again, this is a short little thing. So H alpha paired with E beta, okay, is beta. So the root evaluated on H alpha. So that's a number. Okay. That's the eigenvalue. Multiplied by E beta. Okay. And again, from definition of this pairing, this is this number. Okay. So this is an H, one of these H's in the SL2 theory, acting on a root vector. Okay. We know from SL2 theory that all the eigenvalues are integers. Okay, so therefore this has to be integer. Okay, so from SL2 theory, all weights of H alpha are integers. Okay, so we have this crystallographic restriction. Okay, so that's really important. I'll draw some pictures shortly, but yeah, let me formulate this, how it's related to this, something that you could picture on the root diagram. Okay, what does this value mean? Okay, so there's something called the root string. Okay, so this is really crucial for like classifying these which diagrams are admissible, okay, as which Dynkin diagrams are admissible. Okay, so that really comes up in that proof. For now, I'm just going to formulate this notion of a root string and then draw a picture to show you just visually what's going on. Okay. So let's alpha be in here and beta be over here. The alpha string containing beta is basically you start out from beta, and then you start shifting by alpha. Okay, so take all possible integral shifts by alpha, okay, through beta. Okay, but I want to intersect. I don't want to consider all of those. I want to consider those that are actually in that are actually a root or possibly zero. Okay, so that's this alpha string, and we're going to picture it. Okay, so the alpha string. But basically, the relevance here is this is corresponding to an SL2 rep inside G. For the SL2 spanned by this triple that we've been talking about above. Okay. So you're going to have a bunch of dots, right? So the picture is you're going to have beta plus alpha. Oops, let's not go too far. Beta plus 2 alpha, etc. And then similarly on the negative side, let's put at least one of them here. Beta minus alpha. Okay, so you have all of these dots, but there's only a certain number of those that actually live in the root system, possibly zero. Okay, so how is that related to this number that we have over here? So that's this proposition, and then I'll draw some pictures. Oops. So the alpha string, so containing beta is of the following form. Okay, so basically, there's not going to be any holes. Okay, so you're going to go up to some maximal positive, non-negative integer, q, so beta plus q alpha. And then you're going to go also in the negative direction, okay, the most negative one being beta minus p alpha. And from these two extremal ones, you have all the ones in between. Okay, there's no holes there, nothing missing. Okay, where p minus q is this magic integer in the crystallographic condition. Okay. So let's put up some pictures just to make this really concrete here. Okay. Actually, I want to put a little bit more of a note here. Let's just yeah, I want to put a little bit more of a note if you want to specialize this to the simple roots. Okay. Right. So just to state what this is saying. So you have these two numbers, P and Q. Okay. If I take their difference, then that's equal to this magic number, beta alpha check. Okay. Let's specialize it to the simple root case. So if beta is alpha I, and alpha is alpha j, if these guys are distinct. So first of all, if I start taking differences, so I start going in the negative direction. Okay, so we want to start asking, okay, is alpha I minus p alpha j, p being a non-negative integer, is this ever a root or zero? Okay, so that's what we're asking with these strings. Okay, and the answer is no, except for p is equal to 0. Why? Because you have this negative here. And remember, the definition of a base says that you have these simple roots, okay? And every root in the root system is a linear combination with integral coefficients of that base, with all coefficients being either non-negative or non-positive. But you can see here, it's a bit of a problem because you have a 1, which is coefficient positive, and then here, this coefficient is negative. Okay, so it's mixed if p is not 0. Okay, so that's a problem. So this is never going to be a root except for when p is equal to 0. Okay. So p is not in the game here. So in this case, for simple roots, we get a simpler formula. So this is negative Cij. Okay, so this negative Cij, right, is giving you the length of one of these strings. Okay, so let's just let's picture that. Okay, so this is the length of the alpha j string through alpha I. Okay, so let's go to the C2 case. Okay, so here we go. C2 is this guy. This is the root system. Okay, the Cartan matrix. So you unfold what the Dynkin diagram well, maybe I'll write down what the Dynkin diagram is. So the Dynkin diagram looks like that. Okay. So you unfold from that what the cartel matrix looks like, and it looks like that. So C12 is -1. Okay, so that's this guy. C21 is -2. Okay. So and let's forget this right now. So what does this result say there? Okay, so let's deal with the alpha1 string through alpha2. Okay, so right, the alpha1 string through alpha2. So I should be looking at this one. Okay, so yeah. Okay, so this is -2. So that's telling me the alpha1 string through alpha2 is of length 2. Okay, so you have this alpha2 plus alpha1. Then you have this alpha2 plus 2 alpha1. Okay, so this 2 there, flipped with sign, is corresponding to this corresponding entry in the cartel matrix. Whereas this one, the alpha2 string through alpha1, okay, does it, well, we have a -1 here. Okay, so here we start here, that's our beta, and then we shift by alpha2. Okay, this is alpha2. But it's only of length 1. So this is alpha1 plus alpha2, and then you stop. You could do other things rather than just deal with simple roots. You could go through, for instance, -alpha1 minus alpha2. Okay, so if you do this if you consider the alpha1 string, okay, so you shift like that, or you shift like this. Okay, then in this case, P is equal to 1 and Q is equal to 1. Okay, so you would get 0 here. And you can confirm that if you take this pairing, then you do get 0. Okay, so determining what P and Q are in this case where you don't start out with a simple root, you need more information, really. Okay, whereas in the case of dealing with strings by simple roots, through simple roots, that information of the length of the string is obtained directly from the cartel matrix. Okay, so you get some information about what these parts of a root diagram start looking like, right? It's really, everything's composed of SL2 representations, right? I see SL2 representation there, SL2 representation there, SL2 representation there. All these strings, okay, for certain SL2 triples that are embedded into the ambient semi-simple Lie algebra. Okay, so a couple of other results that I'm not going to prove. So for all roots, the dimension of the corresponding root space is 1. And if I start asking, do I have any other multiples of alpha other than just minus alpha? Okay. Yeah, actually, I guess here we're not formulating for minus alpha. Just any other positive multiples of alpha, are they roots? And the answer is no. Okay. Very much the simpleness condition comes in showing this. Okay. So you never have, so here's a root, you never have any other stragglers out there. Okay, multiples like that. Second result, if alpha and beta are roots or 0, and these are not opposite to each other, then we've seen before that G alpha pairs with G beta to be contained in this, but in fact, it's equal. Okay, and again, simplicity is important here. Okay, so yeah, so you can get some direct information from the diagram about this via vector addition. That, so for instance, this paired with this, okay, or rather the corresponding vectors in the root spaces. So if I take a root vector over here, bracket it with a root vector over there, then you get something non-zero over here. Okay, so we see that just by by vector addition, that this plus this is equal to that, and yeah, that's indicative of what's happening at the bracket level. Okay, because of this equality, that you're actually getting something non-zero. Okay. I think let's take a break right now. We'll go into the formulation of abstract root systems after the break and draw some more pictures. Okay, so we've seen some nice properties of these root systems. So let me axiomatize some of these properties. So something called an abstract root system. And then I'll mention a couple more results, including this business about angles. Okay, so and how restricted things are in this setting. We get some very special structures here. Okay, so first definition. So given a vector space, a real vector space, finite dimensional, okay, with an inner product, okay, an abstract root system, or ARS, is a finite set of non-zero vectors such that we have a few conditions. The real span of these of delta, okay, roots, is all of V. Second condition, given a root, we have we take multiples of that root. So you ask, is this a root? Is C alpha a root? And the answer is if and only if C is plus or minus 1. Okay, this is an axiom. Okay, you don't have an extra redundancy, extra multiples, okay, other than plus or minus 1. Condition 3, very important condition. If you have two roots and you consider the reflection of one in the corresponding wall associated with the other, so alpha perp. So if I take the reflection that we've defined before using this formula like this, then the result is that this stays in delta. Okay, so the set of roots delta is invariant under these root reflections. Okay, so here, where alpha check is this usual formula like this, and we call this S alpha reflection in alpha. Okay, so a bunch of roots that are invariant under root reflections. And lastly, this condition that came up in our calculations above, namely we have this crystallographic restriction. Okay. So these are the axioms of a abstract root system. ARS. Okay, so what we've been led to up to this point is that for any complex semi-simple Lie algebra G with a chosen Cartan subalgebra, this data of this real form in H star equipped with this inner product and equipped with these roots. So this is an ARS. Okay, it satisfies all these conditions that we've axiomatized up here. Okay. But yeah, so I mean, this is just a nice way of like, so we went through a lot to get to this statement, right, as you've seen before. Some people that just want to study the properties of root systems, you could just axiomatize and start from here as your starting point, and then away you go. Let's try to classify these types of objects. Okay, but for us, right, it has the extra bonus that it's going to help classify Lie algebras. Okay. By starting in this abstract root system setting, you could define what the Weyl group is, not in terms of normalizer mod centralizer, but it's the subgroup inside the orthogonal group of V. It's a subgroup generated by all these root reflections. Okay. So yeah, this Weyl group is going to be a finite reflection group. Okay. We know that the Weyl group that we defined previously via normalizer mod centralizer is going to be of this form. Okay. Okay, second definition, as far as breaking things apart, okay, so into smaller pieces. This data is reducible if your space decomposes into an orthogonal direct sum of two smaller spaces. And every root is either in V1 or V2. Okay. Otherwise, it is irreducible. Okay, so this is basically corresponding to like for us, for semi-simples, the cases where you are semi-simple and not simple, right? That you could break it apart into, or in terms of Dynkin diagrams, you have different connected pieces. Okay, so pieces that are disconnected for each other, yeah, you could think of being associated to different factors in this decomposition. Okay. Yeah, and so define base, partial order, Cartan matrix, Dynkin diagram, fundamental weights, everything that we had before carries through in this setting as well. Okay. So let me just put up one result about angles. Okay, so let alpha and beta be linearly independent and separated by an angle theta. Let R be the ratio of length squared of one over the other. And suppose that you put the bigger one on top. Okay, so R is greater than 1. So then you have a couple of possibilities. Alpha is orthogonal to beta. Or things are highly restricted. So you have R being 1, 2, or 3. and theta, pi over 3 or 2 pi over 3 in the first case, pi over 4 or 3 pi by 4 in the second case, or pi by 6 or 5 pi by 6. Okay. Okay, so let's specialize to a base. So specializing to a base, then for I not equal to j, and the Cartan matrix given here is going to be one of these values. Okay, so theseCij's, when I is not equal to j, okay, has to be either 0, -1, -2, or -3. If non-zero, then okay, let's do this again. Oh, sorry, I left two different people. So okay, so we have all these different possibilities for yeah, so remember this number is the indicating the multiplicity of the bond between I and J. Okay, so you have three possibilities if they're actually connected. So it's either 1, 2, or 3. And then the angle between alpha I and alpha J is, well, it's always obtuse. Okay, so that's part of the base definition. Okay, sorry, that's not exactly part of the base definition. Rather, it's a consequence of the base definition. Okay, and the corresponding ratio of the length squared are 1, 2, or 3, respectively. Okay, so mark here obtuse angles. Okay, again, this is very short, so let's just let's start with the general case. So suppose these are not perpendicular. So the angle theta, let's shove it into cos squared. Okay, actually, let's put that up here. Okay, so you're not 90 degrees. So therefore, the cos squared is not 1. I'm going to multiply by 4. Okay, you'll see where this is coming up. Okay, so cos squared is computed by taking alpha beta and dividing by alpha alpha, beta beta. Okay. So I need a square in here. Yeah. Okay, so the 4 is there because I'm going to break it up into 2 times 2 so that I'm getting one of these co-root expressions coming up. Okay, so this is alpha beta check beta alpha check. So remember, alpha check is 2 alpha, 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 similar for beta. Okay, so this 4 was broken up into 2 copies of 2 and then distributed. Okay, to get this beta check and alpha check in there. Okay, but here's where that key crystallographic condition comes in, right? These are integers. Okay. So you have 2 integers that multiply to something that is strictly less than 4. Okay. And so this product has to be 0. Oh, sorry, we're not in the 0 case, right? Because alpha and beta are paired to be non-zero. So 1, 2, or 3. And in these corresponding cases, so this R, which was alpha, alpha, beta, beta. Okay, again, I could do a little trick of getting some coroot to come in there, right? So like this. Okay, so basically I've inserted this alpha beta, which by hypothesis is non-zero. Okay. And then those factors of 2 cancel, but those extra denominators, yeah, are there. Okay, so you can check that this expression is equal to this expression right here. Okay, so under this restriction, right? So you have, well, if this is 3, then one of these has to be, well, you have like 1 and 3 or -1, -3, right? It's heavily restricted. But in those cases, you could check that this has value restricted to be 1, 2, or 3. So, and then we get the first result. Okay. Next, for the simple case. Okay, so you use the formula for root reflections. So we know that alpha j under this root reflection by S alpha I, so this is what it is, by the RS3 axiom, this is still a root. Okay. So, well, this is a root, and by the base definition, so this all coefficients, well, this is a linear combination of the simple roots, and the coefficients, in this case, you have one that's positive, so these guys have to be also non-negative. Okay, so therefore, Cij are non-positive, okay, by base definition. Okay. So if you just use these results combined with what's up here, right? So if this product, for instance, were equal to 3, then yeah, assuming that beta and alpha are these simple guys, then one of them would have to be -1, the other one have to be -3. You cannot have 1 and 3 as a possibility. Okay, so -1 and -3, or -3, -1. Okay. Okay, so yeah, key thing here is for simple roots, right? We have obtuse angles. Obtuse angles. Okay. So let's draw some pictures. Okay, so here there's a lot of detail, right? But when you see all this detail, you have to understand that everything is coming from these diagrams. You're just unfolding it into all the information that entails from it. Okay, so let's just go to this G2 case. Well, I haven't defined in the notes really what the Lie algebra is. There is going to be this theorem reconstructing the Lie algebra from this guy, the so-called Serre theorem, which I'll get to eventually. But for now, okay, this encodes this Cartan matrix. Okay, we know that Cartan matrices always have 2's on the diagonal. And then here, well, the product of these off-diagonal things is 3, and they're integral, and they're negative. Okay, so where do you put the -1 and where do you put the -3? So remember, so here the second guy is longer than the first, and we have this result that's in this case, right? I guess would be C21, C12. What's it 2? Like this. Okay, so this would be square root of 3. Okay, as in alpha 2 is the longer one. Okay, so C21 has to be bigger in magnitude than C12. Okay, so that's why you put a -3 over here and a -1 over here. Okay, so from this, you get the Cartan matrix, you get the inverse Cartan matrix. Remember, you have alpha I is equal to this Cij lambda j, and then you use its inverse over here. Okay, so you get all this data. There's formulas. I don't expect you to remember this, but you could reconstruct all of it from this Dynkin diagram. Okay, so let's just get to the pictures here. Okay, so it's always good to start with SL2 case. Okay, here, yeah, we spent several weeks on this, but just in terms of what we've seen since then, right? So what we have here, this is the weight lattice. Okay, SL2, okay, the adjoint representation. Okay, so namely when we let SL2 act on itself, you know, the x, h, and y. So x has weight 2 we saw before. I've labeled it by alpha 1. Okay, so it's just a slight difference of perspective. Before we were talking about the integers 2, 0, -2. Now we're talking about functionals. What is this functional? It's the functional that on that chosen h, it's 2. Okay, so on lambda h, it's 2 lambda. Oh, I shouldn't use lambda because lambda is always a weight for me, but this is just a number. Okay, so we know how this functional is yeah, maybe that's confusing. I'll get rid of that. If you know the definition of alpha 1 on a single element, then you know what it is on the one-dimensional span, the span of this, the subspace spanned by this element. Okay, namely fract H, the Cartan subalgebra itself. Okay, so we could talk about this functional alpha 1. Okay, but really it's associated to this number 2 that we were working with before. Okay, so yeah, so if you want to look at the root lattice, then it's all integer, it's the lattice 2z. Okay, so you have 0, 2, 4, 6, and then also on the minus side, -2, -4. Okay, so that's coarser than the weight lattice. So the weight lattice is at these integers. Okay, so lambda 1, the highest weight for the standard representation, C2, which we also think about as 1, okay, is this guy here. Okay, this is lambda 1 is the functional that on this specific h, it is 1. Okay, so this is the positive root, this is the negative root. It acts on the weight lattice. Okay. Okay, so let's go to A1, A1, also SL2, SL2, C. We're doing everything over complex. Okay, so here we have 2 copies, one in this direction and then one in this direction. Okay, they are orthogonal. The corresponding Dynkin diagram right? These are not connected. That's indicating an angle of pi by 2 between the corresponding simple roots. So yeah, so this is we're using the weight lattice here. So here are the fundamental weights. The corresponding alpha i's, there's a 90-degree angle over here. The region between, so this lambda 1 direction and this lambda 2 direction, this is the fundamental Weyl chamber in this case. And so there are, in this case, 4 chambers. And the corresponding Weyl group is of size 4. It acts simply transitively on the Weyl chambers. So the Weyl group, well, yeah, for SL2, the Weyl group is just Z2. What is that? It's the flip in the origin, okay? Namely, passing to negatives. So this gets flipped to that. Right. It's, yeah, it's passing to its negatives. Okay. So interchanging also your notion of highest with lowest. Okay. Sorry, I was not finished over here. So the Weyl group is Z2 cross Z2. In this SL3 case, so we spent quite a bit of time on this, right? So these are the positive roots, the negative roots. Here is your Weyl chamber. Let's go to a more, and the, yeah, so the Weyl group is, yeah, S3, the symmetric group. Okay, so, right. So in this case, a more unfamiliar case. Okay, so here, let's get it oriented. Here's alpha 1, here's alpha 2. Okay, the angle between them is 3 pi by 4. We saw that earlier. Right? We drew the root diagram before, but now I've placed the fundamental weights. Okay, so you see that, so we have 1, 2, 3, 4, 5, 6, 7, 8 Weyl chambers. Okay. So this is a dihedral group. So D4 in, yeah, dihedral group notation. Okay. Not to be confused with the complex simple Lie algebra D4. Okay, so symmetries of a square. G2 case, this beautiful diagram over here. And so here's alpha 1, here's alpha 2, angle of 5 pi by 6. Lambda 1 is over here, lambda 2 is over here, and here's the fundamental. Okay, so you have 12, Weyl chambers, you have dihedral 6 for your Weyl group in this case. Okay. Yeah, just to emphasize where these walls are at. So remember, these walls should be perpendicular. Yeah, so perpendicular to the roots. So if I take alpha 1 is over here, the wall alpha 1 perp is right there. For alpha 2 perp is over there. Okay, so we're dealing with the region in between those walls. Okay, alpha 1 perp and alpha 2 perp. Same thing over here. So alpha 1 is there, alpha 1 perp is there, alpha 2 is there, alpha 2 perp is over there. Okay. You can start going to higher dimensions. So in rank 3, there's 3 irreducible abstract root systems of rank 3. Rank 3, sorry, yeah, I don't think I wrote down. So rank here for these root systems is, as usual, the dimension of V, okay, or yeah, the dimension of your Cartan subalgebra. Okay, so you have A3, which is SL4, B3, which is SO 2 times 3 plus 1 is the formula from, yeah, so SO7, and then C3. So SP of 2 times 3 is 6. Okay, so here are their dimensions, here are the number of positive roots. But these were what those zone tool figures that I brought at the gathering for you to just have a quick look at. Yeah, unfortunately, it took a while to get to here, but these are what they look like. Okay, these nice root systems. Okay, so here are the corresponding Dynkin diagrams, and just stare at these for a little while and try to identify what the simple roots are. Now here they've been labeled actually, okay, but just convince yourself that you know what this is meaning. So here, this corresponds to alpha 1. So this guy over here, 1, 0, 0. This guy over here, alpha 2, is 0, 1, 0. And this guy, alpha 3, corresponds to 0, 0, 1. So the existence of this bond, well, actually, let's start with this guy and this guy. There's no bond between them. Okay, so these guys are orthogonal. So if you look at this guy and this guy, that's at a 90-degree angle between them. Whereas if you take these two, so alpha 1 and alpha 2, so this guy and this angle is 2 pi by 3. Whereas this guy, that's also a 2 pi by 3 angle. In the next diagram, okay, so you have alpha 1 over here. So this guy and this guy are long, and this guy is short. Okay, this points in the direction from long to short. Okay, so these guys are not connected. So this guy and this guy are at a 90-degree angle. Okay. Over here, this is at an angle of 2 pi by 3. So that's this angle over here. Whereas over here, let's see, 0, 1, 0. Yeah, from this guy to that guy, that's a 3 pi by 4 angle. It's kind of hard to see it in this projection. Yeah, it's nice to have those three-dimensional figures. This guy for C3 is actually very, very similar to this guy. The directions in which all these roots are arranged is actually the same. What's different is your notion of long and short. So here, this light blue guy is short, and most of the other ones are long. Here, it's the opposite. The light blue one is long, and the green ones are short. Okay, there's actually in general between Bn and Cn this extra discrete symmetry. Namely, for any root here, I could get to a root over here via what's called, well, the co-root operation. Okay, so this is not obvious at all in general, but it can be shown that if you have any one of these roots in the Bn root system, so for Bn root system, then you get something in the Cn root system, but it interchanges long and short. Okay, so short goes to long roots go to short roots. Okay. So yeah, so these are the three irreducible abstract root systems in dimension 3, rank 3. Okay, so of course there's a lot of details to still, well, actually it's not that much longer. So the proof of the classification of simple Lie algebras. So you classify admissible, well, actually, you're really classifying these irreducible abstract root systems. Or effectively, you're classifying connected Dynkin diagrams. Okay, so it's actually, I think, only 3 or 4 extra pages of in this Humphreys book. Humphreys book, theorem 11.4 there. Okay, so if you're interested in the details there, do have a look at that. Okay. Okay, but you get some really nice, beautiful, symmetric geometry coming out of these Weyl groups and these root system objects. Okay, I want to mention one other really nice way of visualizing Weyl chambers. Okay, so in the two-dimensional case, and you have these things that I've colored in over here, right? And you can see they're mirrors in these walls. So here's another one, here's another one, et cetera, et cetera. Okay, so one way to do this in higher dimensions, or in particular in dimension 3, here's what we're going to do. And I'll just illustrate the construction in dimension 2 first, so that we can see what happens in dimension 3. Okay, so in dimension 2, let's just take, for instance, this guy. So what we're going to do is that for any root, okay, we're going to consider the corresponding wall. Okay, and we're going to take that wall. Wall, and we're going to intersect it with a sphere of some fixed sphere. Okay, so I'm going to take a sphere, let's say that one, and then we're going to intersect it with one of these walls. Okay, so that's in this dimension, it gives me 2 points, this one and this one. But we're going to do that for every root. Okay, so for this one, we have this wall, okay, and we're going to get another 2 points. But basically what that's doing is in the sphere, it's marking several points, okay, and basically chopping up the sphere into these sectors. Okay, each of those sectors is representing a corresponding Weyl chamber. Okay, so instead of viewing the Weyl chamber like this, I'm viewing the intersection of the corresponding walls in that fixed sphere. So I'd be viewing this as an arc. Okay, so it doesn't look so pretty in 2 dimensions, but in 3 dimensions, it's actually really cute. Okay, so have a look here. Okay, so let's see. Just a sec. I'm gonna write a little note here first. Walls and spheres. Okay, so fix a sphere. Okay. Centered at the origin. For each root, alpha perp intersected S. Okay, this is a great circle. Okay, in 2 dimensions, it's just 2 points, right? But 2 points is the sphere in one lower dimension there. So here, this is a great circle. Okay, the sphere in 1 dimension. Okay. Okay, so this is a great circle on S. Okay, so do this for all roots. Okay, and so what you're going to get are these pictures right here. Okay, so each of the sphere is basically, this fixed sphere S is cut up into all these sectors. Okay, and each sector corresponds to a Weyl chamber. The Weyl chamber actually starts at the origin and kind of extends out to infinity, right? So this is just the intersection of that Weyl chamber with this fixed sphere. But this gives us a way of visualizing these Weyl chambers. And in particular, in here, you do the count of how many Weyl chambers you have. And I think, yeah, you get 24. Okay. Here you have 48. Here's something more interesting, okay, which, yeah, you get, oh, I forget the count for this one. 120, I think. Okay. These are the Weyl chambers of the A3, B3, and so-called H3 root systems. Just a bit of a warning, however. So here I've put B3, but it's actually also C3 Weyl chambers at the same time. Remember, I mentioned how you have this transformation, so passing to the co-root, right? So, but in this construction of these walls and spheres, when you take walls, you lose information about lengths, right? You're just interested in the perpendicular to these roots. Okay, so it's not going to make a difference whether I consider alpha or alpha check. Okay, so these guys under the construction that I've just given give you the same results, namely this one. Okay. So the Weyl groups in this case, for instance, so the Weyl group of A3, this is called the tetrahedral group. In this case, a group of B3, this is the octahedral group. Okay, and these guys are the discrete, are all the symmetries of, the first one is the symmetries of a regular tetrahedron. The second one is the symmetries, okay, of regular octahedron. And at the same time, it's the symmetries of a square, a cube. Sorry. Of a cube. Okay. This last one, the Weyl group of H3, this is called the icosahedral group. Okay, so symmetries of the icosahedron or the dodecahedron. Okay. Now, if you remember from the classification of simple Lie algebras, some warning bells should be coming up, because there wasn't any H3 there. Okay, so we had, for the exceptionals, we had G2, F4, E6, E7, E8. There wasn't any H3 here. Okay, so why have I put it over here? Well, this is something that's not corresponding to a Lie algebra. Okay, the groups here, these finite reflection groups that come about, these Weyl groups, they're all finite reflection groups, and the broader setting for this is that of Coxeter groups. Okay, so what we have here is something that is a Coxeter group, but it doesn't, it doesn't satisfy that crystallographic restriction for the corresponding root system. Okay, but you can still talk about a weaker notion of root system. Just forget about that crystallographic restriction. And there's a few of these that come out in the classification. There's only a few beyond the ones that come from simple Lie algebras. And one of them is this H3 guy. Okay. So you still get some beautiful figures coming up, even without that crystallographic restriction. But again, there's only a few of these. Okay. Some of you this might be familiar to some of you, this pattern. Okay, some of you might have seen it before. Let me see if I have that here. No, okay. So some of you might be familiar with this company called Brilliant. So it's a nice, if you haven't seen it before, just click on it right here. It's a nice resource for math and science. They have all these courses. Sorry, this sounds like an ad, but it's interestingly enough, the point was that the logo is exactly this associated to this H3 root system. Okay, presented in this way that I've talked about. Namely, what you're visualizing here in this picture are the Weyl chambers for that H3 system. Okay. Okay, so we are at the hour. I think let's take a break at this point, and we'll see you in 15 minutes. Okay, so in this last part, I want to do two things. One is just formulate the Serre theorem to that's starting from the data of Cartan matrix or starting with the data of the Dynkin diagram. Then to reconstruct the Lie algebra. Okay, so how does that look in terms of corresponding generators and relations? Okay. So that's the first part. And the second part is discussing this theorem of highest weight. Essentially, all the ingredients are there, just kind of giving some more examples in this broader setting of semi-simple Lie algebras. Okay. So for this first part, okay, so I want to mention this notion of a so-called free Lie algebra. So given a set X, we could talk about some free Lie algebra L of X. So this is a complex Lie algebra generated by a set X without any imposed relations other than the minimal you need for being a Lie algebra. Okay, so other than bilinearity, skew symmetry, and of course, Jacobi identity. Okay, so in general, yeah, so you can show that this free Lie algebra on a set X, right, it's unique. And in general, it's infinite dimensional, okay, if the size of the set X is at least 2. Okay, so just as, yeah, so I'll just put in some notes here. Let's just go through it. As an example, if you have X consisting of the 2-element sets, then L of X consists of all those finite linear combinations of objects that look like this. So E1, E2, you have this symbol bracket E1, E2, okay, which you're taking to be linearly independent from these two, okay, right, without any imposed relations. Okay, I'm saying it slightly loosely here, but yeah, so this is linearly independent from these guys. You start taking further brackets. Okay, brackets, brackets, further brackets, okay, et cetera, there's infinitely many possibilities, right? But of course, you want a Lie algebra, so you're imposing the minimal amount you need, bilinearity, skew symmetry, and Jacobi identity. Okay, so you have this really big Lie algebra, infinite dimensional, L of X. What can we do with it? Okay, well, so here's the amazing results. Let's start with the Cartan matrix of an irreducible abstract root system. Okay, so we don't know yet that it comes from a semi-simple Lie algebra. Okay, so we have some, we have the axioms that we know about irreducible abstract root systems, and then we could talk about its Cartan matrix. So these satisfy some conditions, of course. So that suppose you have one of these, then take the free Lie algebra generated by the following elements. So you have X, H, and Y. Okay, you have L of those triples. Okay. So these are going to be the SL2 triples associated with some simple roots. Okay, and there's L simple roots. Okay, so inside this free Lie algebra, we're going to create some ideal. So give it a bunch of relations. Okay, so these are the so-called Serre relations. Okay, so I'll get to motivating this shortly, but if you take the quotient, okay, so this free Lie algebra modulo all these relations, turns out this is finite dimensional, and it turns out it's a finite dimensional simple Lie algebra. These H's will span a Cartan subalgebra, and the alpha J's defined by, well, alpha J on HI is this CJI. So these guys form a simple root system. The Cartan matrix of that is exactly the one that you started out with. Okay. So let's go to these relations. So the first one, well, these H's, they're going to span a Cartan subalgebra, so these guys should commute with each other. Okay. This Cartan subalgebra is abelian. Next, if I bracket an X with a Y, I'm going to get some H. Okay, but so Xi and Yi, so within the same SL2 triple, is going to give the corresponding Hi. If X brackets with a different, so with a Yj where I is not equal to J, you're just going to get 0. Okay, so those guys from different SL2 triples corresponding to simple roots, they don't interact. Okay. This is the X's and the Y's. Okay. Take an H and then let it act on an X. Okay. Then you get CJI XJ. Remember, if I is equal to J, then you have a diagonal element of the Cartan matrix, which is 2. Okay. But otherwise, you get potentially some interaction. Okay. Similarly for the Y's. Okay. With opposite sign. And then lastly is a statement effectively about root strings. Okay, so if I let the X's interact with each other, okay, so this is the raising operator corresponding to alpha I. This is the root, this is in the root space for alpha J. Then how long is that corresponding root string? Well, after a certain number of applications, you get to 0. Okay, so if I take away that 1, then it's a root string of length minus CJI, which is related to the root string stuff that we talked about earlier. Same thing with the Y's. Okay, so these are all quite natural relations, but what's remarkable is that this is all you need. Okay, so aside from these natural relations, yeah, that's it. So you do this quotient construction, and then you end up with the original Lie algebra, okay, or a simple Lie algebra with this guy as your seed data. Okay, this Cartan matrix. Okay, so it's a remarkable result that basically closes that circle of ideas, right? We started out with a semi-simple Lie algebra. You got to a Cartan matrix modulo of 2 choices, but this allows you to reconstruct that original Lie algebra, simple Lie algebra. Okay. Okay, so nice, beautiful result of Serres. Okay, so let's now pass to the theorem of highest weight. And really, it's the exact same statement as before, what we had for SL3, except now we're just stating it for general semi-simples. The construction of general representations is done as before. You try to construct the fundamental irreps. And then from that, you look inside a certain tensor product of those for the irrep that you're interested in. Okay, so whoops. Once the fundamental irreps, so V lambda I, are known, constructing V mu, where mu is a linear combination of those lambda i's, is done as before. Okay, so look at V, which is here. It's L. Okay, remember, we're working with dominant integral weights. So that means these Ri's, are dominant integral. So non-negative integers. So this construction over here makes sense. Okay, so I'm going to look inside there, and then I'm going to look for the highest weight part sitting inside that. and then use that to generate this representation. Okay, so you take a highest weight vector, okay, and then we act with G on that highest weight vector to generate this representation. Okay, so the question boils down to understanding what are these fundamental EREPs. So I just want to give you a survey of what these guys look like for, at least for the classical guys. Okay, so for A3, which is SL4, okay, so here, Cartan matrix looks like that. Dynkin diagram looks like that. Okay, so what are your fundamental EREPs? Okay, so here's highest weight. Here's a highest weight. And here's a highest weight. Okay, so lambda 1, lambda 2, lambda 3. Oh, okay. So in terms of the epsilons, so lambda 1 is epsilon 1. Lambda 2 is epsilon 1 plus epsilon 2, and lambda 3 is epsilon 1 plus epsilon 2 plus epsilon 3. The realization, so concretely, of this representation, this is just the standard representation. Okay. We've seen that epsilon 1 is the highest one for the standard representation. Epsilon 2 is the next. So if I know that I'm looking for a representation with highest weight epsilon 1 plus epsilon 2, one should look at this wedge 2. Okay, and it turns out that's correct, that this is irreducible, and that is the highest weight. And you pass to wedge 3 for the next one. Wedge 4 of C4, that's one-dimensional. Okay, so we don't have, that's just the trivial representation. Okay, so for the general picture for type A, it's similar. So for AN, which is SL n plus 1C, okay, so you have n of these dots, okay? The kth fundamental EREP is generated from the first one through a wedge construction. Okay, so this is the same thing as wedge k of Cn plus 1. On the other hand, we've seen there is another way to write this down. So you have this, let me just write it down first, and it's related to something that we've discussed a few times before. You could relate it also to the dual representation, okay, but you have to change this wedge power, okay. Why is that? So basically, so note this top one is trivial. That's a trivial rep. And you have a volume form, basically. Actually, in the dual. This is the same thing. And we have a volume form. And so, yeah, there's a natural intertwiner. Okay, similar to those intertwiners that we've seen before using volume forms. So namely, what is this map? You insert these vectors into the first k slots, and then you have n plus 1 minus k slots left over. So that's a certain wedge product, okay, of these forms. Okay, but the point here is that, yeah, you have this explicit description for all these irreducible representations. Okay, just as wedge products of the standard one. Okay. Okay, so that's in type A when you have this nice, well, nice, it's called a simply laced diagram. So there's no double bonds. Okay, they're all single bonds over here. Type B and D starts to get a bit trickier. Okay, so here are the Dynkin diagrams. Okay. Now you might suspect that, well, okay, there's a large type A subdiagram over here. Okay, so are the EREPs related? The construction of the EREPs related, at least for those ones. And then some funny business happens for these last couple of nodes. Okay, so it turns out in this case that's so some things are similar for the first ones. Okay, so V lambda 1, this is a standard rep. Okay, let's see, V lambda 1 is a standard rep. Lambda k of, oops. So this is true for those guys, for Bn. It's also true in this case for Dn. Okay, so here the enumeration is 1, 2, da, 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 up until n minus 2 over here. And then this is the n minus first, and this is the nth. Okay, so this wedge construction in terms of the standard one does work over here. Okay, these guys at the end, these guys are exceptional. Okay, so these those guys, that's not an easy story. It's it takes some time to develop those. So constructing this guy for Bn and these guys, it's beyond the scope of the course. So these are the so-called spin reps. Okay, so it involves doing quite a large detour in yeah, talking about Clifford algebras and what the spin group is and how do you construct these spin representations out of there. Quite a nice story, beautiful story, but not that not to be done quickly. Okay, so so this is for the SO odd case, you have a single spin rep, whereas here you have two, sometimes they're called half spin reps or chiral spin reps. Okay, and the vectors in these representations, these are called spinners. Okay, but that's a story for definitely another day. Okay. Type C. Here's the Dynkin diagram. Again, there's a large type A subdiagram. Okay. So this is for Cn, that's sp2nc. But in this case, it's not, it definitely doesn't work. Okay. So note, so above trick does not work. Okay, and so you could see this also just from considering wedge 2 of this. So it is still true that the first one is standard representation. Let me write that down. This guy is standard rep. Okay, so C2n. But wedge 2 of lambda 1. So this is going to be lambda 2, V lambda 2. But then there's a trivial factor here, okay? How do we see this? Well, remember that, well, actually, yeah, I guess I could remember that for the symplectic guys, right, these are defined by an invariant bilinear form. We have an omega, a symplectic form. Okay, that's invariant under Cn. So whenever you have these invariant non-degenerate bilinear forms, you have an isomorphism, an intertwining isomorphism between a representation and its dual. Okay, so I could write this as this. Okay, but here definitely there is a trivial factor sitting inside there because that's omega itself. And it turns out that that's actually the only trivial factor. And then there's an invariant complement that gives an irreducible representation. Okay, so, but beyond that, so I'll do this in a little bit more detail. Okay, so, but let me just tell you the general result. If I start taking these higher tensor powers, higher wedge powers, then I'm going to get the kth fundamental irreducible representation. And then I'm going to get wedge k minus 2 of the standard. Okay, so you could iterate this and get a formula like that. Okay. So the situation is more complicated in this case. Okay, so I'm not going to go into more detail, I think, for that. What I do want to end off with is really just making the C2 case, so SP4 case, more concrete. Okay, so basically, we've looked in a lot of detail for the A2 case, the SL3 case. So let's discuss C2 in more detail analogously. Okay, so if you go back to the root data, okay, then you'll find formulas like this that we saw at the start of today. But you also find lambda 1 and lambda 2 written out in terms of the alphas. And then you could write them out like that. Okay, so as in the type A case, you have epsilon 1 for lambda 1, and lambda 2 is epsilon 1 plus epsilon 2. Looks very similar, right? But yeah, let's just write some more here. So H is spanned by elements looking like that. Okay, the weights would be epsilon 1, epsilon 2, minus epsilon 2, minus epsilon 1. Okay, so this is on C4. Okay, so this is C2, which is SP4C. Okay, so this is good enough to establish that this is irreducible. And yeah, basically you do it as before, how we established those representations for SL2, that those guys were irreducible. Same argument here, okay? It's not too difficult, so I'm not gonna go through it. But yeah, out of this, you get that this is the standard representation, okay? But being in the C2 case here, SP4, so this admits a symplectic form. So an invariant symplectic form, which I'll write as E1, E4 plus E2 wedge E3. Okay, or this is associated with that defining bilinear form, skew symmetric matrix, looking like that. Okay, I take the usual basis E subscript 1, E2, E3, E4 for the weight basis on C4. and then raise the indices to get the dual basis. Okay, so actually, because of this bilinear form, right, we get this identification of C4 with its dual. Okay, so let's now realize this guy concretely. Okay, keeping in mind, well, these weights, these epsilons, okay, epsilon 1, okay, this is the highest weight for this guy, and then epsilon 1 plus epsilon 2. The highest weight vector here is E1, okay, the next highest would be E subscript 2. Okay, so we're going to realize this inside the wedge 2 of C4. Okay, so, and note that the highest weight vector is going to be E1 wedge E2. And this is weight epsilon 1 plus epsilon 2, okay, which is our desired highest weight, lambda 2. Okay, but wedge 2 C4 is isomorphic to wedge 2 C4 dual, and that contains this invariant element, omega. So therefore, this is not irreducible. So how do we construct this? Just as before. So realize this guy by applying lowering operators to E1 wedge E2. Okay, so what are these lowering operators? So remember, we had these these matrices before. So if you look at the matrices corresponding to the negative roots, you're going to get these expressions that I'm writing down right now. Okay, so strictly lower triangular stuff. There's some constraints. Okay, we have 4 negative roots here, and so we have 4 lowering operators. And lastly, this guy. Okay, so right, and these are all written out in the E1, E2, E3, E4 basis. Okay, so these tell me how to act on these guys. Okay, so you can build a little table just as we've done in other examples. Okay, so weight vector, weight. Okay, so top one, E1, E2, E1 wedge E2 with weight, epsilon 1 plus epsilon 2. Okay, so we could start letting it act by derivation, letting these lowering operators act on these guys. Okay, so for instance, this one tells me on E1, it gets sent to E2. So this would be sent to E2 wedge E2, okay, as the first term, which is 0. This, and then you let it act on the second vector, okay, and it kills it. Okay, so this applied to this is 0. Okay, however, this one is going to act on this to be non-zero. It acts on the first one as zeros. It acts on the second one, sending it to E3. So what we're going to get is E1 wedge E3. And you could check that this, yeah, so minus alpha 2 is minus 2 epsilon 2. So that's why this is the weight. And in this way, you just keep going with applying these these operators. Okay, but you're going to find that you get a 5-dimensional space. Okay. And here are the weights. Okay. So everything is reconstructed from that highest weight vector with that known highest weight. Okay. So wedge 2C4 is dimension 6. This V lambda 2 is 5-dimensional. Okay. Another description of this V lambda 2 space is it's in the kernel. I haven't introduced that notation. So we have these wedge 2C4 vectors. So it's a linear combination of wedge products like this. Okay. This particular subspace or subrepresentation is obtained naturally from omega by the following. You take V and W and you shove it into the symplectic form, and you should get 0. Okay, so it's in the kernel of a certain contraction. Okay, that's another concrete realization. So how this is actually embedded into wedge 2C4. Right, so let's see. Yeah, there's the omega, E1, E4 plus E2, E3. And so notice for this one, for instance, if we do the insertion into there, then that here having a minus sign is essential. So insert this into there, you get 1, but you insert into the second one, you also get 1, but here there's a negative. So they cancel. Okay, let's just reinforce this with the abstract picture. Okay, so, whoops, let's try shifting. Okay, so here we've seen this before, C2. Okay, root system, fundamental weights, Weyl chamber. Here's lambda 1 in this picture. Here I've drawn all these walls. Okay, so even though it is coinciding with these root directions, really for each root, I'm taking the perp, okay, to construct these walls. Okay, so as before, if you want to understand the representation where everything lives, you start with the highest one. You start taking reflections in these walls. So this one gives me reflection over here. Reflection in here gives me this one. Reflection in here gives me this one. And that closes up. Okay, so I have an orbit of size 4. And then what's on the inside of the representation, which weights are actually occurring, you have to apply negative, a linear combination of the negative simple lowering operator. So negative simple one is that one. So minus alpha 1, minus alpha 2. There's nothing else inside here, right? That lies on the weight lattice and is the highest one. Subtract an integral linear combination of these simple ones. Okay. So here, this is obviously dimension 4 because, yeah, we've had this multiplicity result that all the weight spaces on the boundary are of multiplicity 1. Here for V lambda 2, we start with this guy. Okay, it's a dominant integral weight. Okay, so lying in the boundary of the fundamental Weyl chamber. We start taking reflections. So here gives this one, here gives this one, here gives this one. So we get an orbit of size 4 on the outside. But in this case, from this, we can get to here. Okay, so namely, we apply minus alpha 1 and then minus alpha 2. So minus alpha 1 gets over there, minus alpha 2 gets over there. Okay. So we've realized this inside wedge 2C4, which is 6-dimensional. So what we've shown in this diagram is at least 4, well, plus 5, okay, dimensional. Okay, so the question is, what is the multiplicity of this thing in the middle, the 0 weight? Is it 1 or 2? Well, because we're living in this wedge 2C4, which is not irreducible, then this is at most 5-dimensional. But so that's telling us that this weight has exactly dimension, multiplicity 1, not 2. Okay. So yeah, so this is the picture for C2 fundamental irreducible representations. Okay. So I think that's pretty much what I had for talking about today. Sorry, I went definitely over time, but hope you guys got some ideas about just, this is a beautiful subject, and there's a lot of really interesting things. We just really touched the surface. It really is used a lot in geometry and many other parts of mathematics as well as physics, Lie theory. And so, yeah, definitely. I mean, if you have an opportunity to learn some more, go for it. It's a beautiful, beautiful subject. I've been at it for a while, but a lot of interesting things coming up.